Okay, so good morning, everyone. Okay, so we are going to continue from last part of the discussion, which is the existence and unique solution. So we have described that for existence, we need to have some like interval of existence if the functions continues around some interval. Okay. And we need to at least having an open interval around x equals a for the interval ab. Okay. And at least on that interval, there will be one solution exists. So we can say that that is the existence of the solution. And if the function is not continuous, solution will not be guaranteed on that point. On that point. And as a note that the endpoint, okay, so x equal a that mentioned in this interval, it can't be the endpoint for the interval itself. Okay. So it should be in between. Okay? So it should be in between of the AB for the solution of the interval. Okay, now let me write here. So before I'm explaining about this graph, let me write the definition of the uniqueness. So if df dy, it means that f is a differential equation, is also continuous, around the interval AB, then the solution to the differential equation at this point AB is we call unique. Unique on open interval around x equal a. We're going to see how do we apply this existence and uniqueness, okay, by checking the interval and the possibility of the solutions. And the graph below is one example. It's one example on how differential equation may have more than one solution. So if I have here dy dx equal x y with power of half, then we may try to verify that y equals 0 and y equal 1 over 16x with power of 4. These two can satisfy, okay, satisfy as a solutions. And then we can set up the initial conditions, that is the point 0, 0. So at the y0 equals 0, we could set up initial value. Okay, we could set up the initial value. So we can set up this initial value. So at the dy dx xy with power of half, and by taking the initial condition, we can see that at least this differential equation have two solutions. And we can see from the graph that at this point here, we can see that we could have this, okay, this curve, or this line here, which they are also crossing the same point. Okay. So based on what we have, as in the definition on existence and the uniqueness, we could at least verify if we have differential equations and then we have a setup for the initial value, initial condition. We could check whether they are first checking they are continuous or not, okay, and then checking the existence of the solution. Okay. Is there exists one unique solution or not? Okay. So I think that will be for a few examples. I will show you how we could see the process. I think some definition of the textbook may look a little bit different because I'm using just words that is open interval around x equal a. Maybe the textbook sometimes they're using the interval with some distance h, but I think that will be the same maybe. I try to make it short. Okay, let me give you a few examples how we could verify. Okay, we could verify. Okay, first, let's say we have a function. And then checking at maybe not y, maybe just f. So we have two variables here, okay. But it's quite it's simple enough. So first is let's try to derive this. So we are going to derive with respect to y. So we have 4x squared y. I hope you still remember how to do it partially. And if we see the configuration of this function and the derivatives, we see that I believe this function is not really complicated, and we could see that we can fit all the numbers, right? So we could say, okay, the functions is continuous everywhere, right? And when we derive this also continuous everywhere, or we say dy continuous everywhere. So we could say that because they are continuous everywhere, of course, when we plug in x equal 1, it should be a unique solution. So at there exists one unique solution. Okay? Okay, give you another one. So this is just checking the interval, okay, whether it's continuous, and then maybe looking at the domain, how the function will be. And another questions, let's say we have dy dx equal x ln y, and then we have the initial value. So the point is 1 1, right? Okay. This point is here is 1 negative 1. I forget to write. Okay, and then let's say we are going to define this as a function of xy. We can do that. Okay, we could just let this differential equation equal to this just a function, and then write x ln y, and then we can derive this with respect to y. So we could say that we can have x over y. Okay, now by taking the logarithmic, by this logarithmic here, now we have some certain domain, some certain interval. If you want to make it continuous, then we could say here the f continuous when y is positive, right? So we say that it will exist if y is positive, okay? And now if we look on, if we derive this and then see the continuity, we could see also this derivative is continuous when y is not 0, right? But at this point here, since this is positive, right, it's already greater than 0, so we could say still this exists one solution. But if we observe maybe 0 or maybe negative, then perhaps we cannot guarantee. Okay, so we can say since this is in a positive value for the point, since is greater than 0. Okay, so add on 1. There is one unique solution. So basically what the existence and the uniqueness say that is basically we are going to try some intervals, and then we are going to observe whether the function or the derivative of the function is continuous or not. Okay. So let me write some notes here. So if y is 0 or y is less than 0, so we can say this is not guaranteed. Okay. Okay, one more example. Also a little bit review on the partial. So dy dx equals square root of x minus y, and then we have initial conditions 2, 2. So the point is 2, 2. Okay. Okay, first we can let this as a function of xy because we just want to observe. Okay, we want to observe. So we can let this as a function. Although the function itself is already in differential equation dy dx, but we want to observe in terms of the right side of these equations. So this is x minus y. Now we are having some restrictions now because we don't want this to be negative, right? If we want to make it a real numbers. So we say that this will be continuous if, or maybe for, x minus y, this should be greater than 0, or x should be greater than y. We have some restrictions now for the functions. And then we take, should be dou f dou y. I forgot to write, we need to have a special Leibniz for the partial. Okay, so Do you remember how to derive this? Do you remember? No? You just take it like a regular derivative. Like you have like square root of x, you will have 1 over 2 square root of x, right? But when we have this, and then we are going to derive with respect to y, it means that we are going to have a chain rule with y. So we are going to multiply with derivative of y, which is -1. So -1 over the whole thing here. Okay? Got it? I'm trying to make it fast. But I hope you still remember, okay? I hope you still remember. But if you still have some struggling there, you need to have a review, okay, on your own. So this is -1 square root of x minus 1. 2, sorry. And of course, from this part, then we need to make this greater 0, because we need to make it not negative, and then we see that it is in the denominator, which is not equal to 0. We need to have x minus y is greater 0. So we say that at two, what will happen at 2, it's equaling to 0, right? It's equaling to 0. Okay. So at 2, we cannot guarantee the existence. So basically, this is just an overview or some quick review on how to look on the continuity of the function. Okay. Basically, most of the time, if there is something trouble, at least 3 kind of functions that can be a problem for you. Okay. First is we have the square root. Of course, we have some specific interval. Okay. Or we have the reciprocal, 1 over something. And then we have the logarithmic. Then we need to have a positive, right? So I think just 3 special cases most of the time, since you learn like calculus or from your mathematics, basic mathematics, those 3 will have special cases that you need to be taken care of. Okay, is for, I think they are all the introductions. Okay, I will skip there are some mathematics modeling, like using some models with for example, to describe the population, radioactive decay, the Newton's law, spread of disease, chemical reaction, and others. But I think I will skip that for a while and focus more on the techniques and before techniques, maybe some parts on what we call the directions field. Okay, but that is for what we call the first order differential equations. Okay, we call the new chapter. So this whole part from our first class, it's all the introductions. Okay? So not yet any methods or techniques to find the solution itself. We just verify the solution, whether it exists, whether it's also have one unique solution, okay? And how to categorize the order and so on and so forth, right? Okay. This one I forgot to mention. This is just what we have discussed before: the existence and the uniqueness of the solution. So if we want to take time to see the graph here. So as long as we are in this rectangular shape and we can make sure that the function is continuous, the derivative also continuous, then we can have the unique solutions. So And the interval, they have the distance h, which is similar approach with our calculus. And then they're just saying that if f and the f dy continuous, there exists some interval, and within this interval, it means that what we have written before, if we have the interval ab, then there will be some around x equal a, okay, which means that this interval, okay. And then they contain in this interval and a unique function defined on the interval that is also solutions to the initial value problems. Okay, that's the same thing what we did before. Okay, just quick notes, and let me go. Let me just put here for a while here. Maybe just make the new one here. So I will start with. So this chapter is the first order differential equation. And before we take some methods or techniques, there are some introductory. Okay, so you can see this subtitle here, that this is we can have a solution curves without a solution. So what does it mean? So if we take for example, y prime squared plus 1 equals 0, okay, the solution, you could say, or let me write, no real solution, or no real function that satisfy. Okay. And if you remember what we did before, that we can see that differential equation may possess solution analytically, which means we can set the implicit form or using the explicit form. And we may found this from some procedures, like for, I think the very simple one is the just normal integral. So if we so what does this solution curve means? So if we cannot find through this analytics, or maybe we see that we cannot have any real function that satisfies this one, then perhaps we can just maybe draw. So this is what we call qualitative solution. So we can analyze. So we can analyze solutions of DE qualitatively. And how to analyze is basically implementing what we call slope field. So what is slope field? If we have maybe the magnets, like if I draw like this one, it has magnetic fields, right? Usually we drew like maybe like this. Okay, and then the other part will have something like that. This is just to illustrate how we are going to get our slope fields. We could see that at every point in this magnetic field, we have some kind of like a small line. Now what we are going to do is, basically the slope fields is a field that containing a small slope for each point. So remember that the y over the x represent tangent lines, right? At specific points. Okay, so let me, or we could say slope, right? So the process is, first is drawing a lot of small lines representing slopes on maybe at points x, y. Okay. And then if we know the initial condition, so given initial condition or initial value, then we can approximate the fitting curve. So basically we are going to take some time to draw some differential equation into a slope field. Okay. And then given the initial condition, we are going to see which one of the following like directional fields or slope fields we are going to have our solution. Now, of course, because we have now restrict all the chapter is about the first order, right? And we are going to see that this is the first order, right? Then we can apply this slope fields. Let me give you a quick example on how we can use this. So it's called a slope field, or sometimes called a direction field, okay? Or direction field. Okay, so let me copy this, okay, and you can continue writing on the next page. So let me copy. Okay. Okay, for example, okay, this is what we call, like we have the small line here at the graph here. We call this line segment, we call this the lineal element. And then if we have the initial condition, for example, the initial condition is this 0.23, as you can see from the graph here, then we can approximate, and basically, because we are just observing this small element, then we can probably take our gas maybe around here, but we need to have another point to make sure that our curve is fit with the whole direction field. Okay. So let me show you how we can get the direction fields. Okay. Let me start with the simple equations. So let me start with so example. If you have a dy over dx equal x plus y. Here this is very simple. So how to get it? So maybe we could say we check the interval maybe from -4 to 4. So x equal -4 and x equal 4. And then also checking with the same y, -4 to 4. Or maybe make it smaller, maybe. We could say that. So first we are taking our times to make a table. Maybe 3, okay, maybe 3. Make it 3. So we have -3. So this is for x, this is for y. Okay, and then you could see that if we check, and then we check by just plug into our equation x plus y. So the dy dx becomes, this is -6, it's -5, -4, -3, -2, -1, and then 0. And then do the same thing. 4, 3, and then this will be 4, 3, 2, and because it has a pattern, I think we can go through. Maybe let me make it a little bit clearer. Okay. And then this is -2. Okay. Now the next thing is we are going to, let's say, approximate. For example, this is representing the slope. Okay. Slope equals 0 means that this is a horizontal 0, okay. And then 1 going up a little bit, maybe 2, 3, okay. And then -1 is going down. And we try to fit in with all these numbers into our slope. Okay. So we take the the graph like this one, and then we are going to observe the interval. Let's say -3. So let's say this is 0, 1, 2, 3. And then perhaps we could start with the 0, maybe. So 3 and -3, this is going to be that way. So maybe we have that horizontal tangent. Also in the -2 and 2. And then 1 and -1 also, and then 0, 0, so I'm trying to give you some idea how we can describe this and make your own. Of course, in the reality, it's better to just using some software to make it the graph for you. But I think if you do it like manually, you know how to get this. Okay, at least the process. Okay? And then we could take the we could try from 0, -3, or maybe from 0 to 1. 0, 1 is 1, so we could maybe a little bit there for 1, and then 2 is maybe twice more, like that, and then 3 maybe getting increase and increase. Okay. So this is the same thing. This is 1, this is 2. I mean the slope equal 2, right? And then this also the same. Okay. And then basically you could fill in all the slopes. Okay. And maybe we could try also finding the negative one, like this one. This is -1, -2, and -3. Okay. And you could fill in all the information within this 3, -3, 3, -3, x, y interval. And you can see that we could somehow try to fit some curve. Okay? It's not necessarily to be directly need to be all the slope necessarily to be get in contact with the solution curve, but you can see the patterns. Like you can see the pattern, like it seems like it has like this kind of curve. Right? So perhaps that is one curve that you can approximate. Okay? And this is just approximation there. Okay, using the graphics. Okay? So maybe we can say that okay, maybe we can have this, okay? And then it depends on our initial value. Maybe if we have initial value maybe 1, 0 maybe here, then perhaps this is the curve. Maybe this is the curve. Okay, and we could see and then check with other slope fields as well. Okay, I'm also checking some informations on to give you more idea what we can have, because I checked some website, they have a good informations and good graphics. Let me check. Okay, you could try to do it on your own, filling all the this field. But what I want to show you, let me change the screen for a while. And see, in GeoGebra, you could type in the slope fields. Okay, so this is one example. The equation here is x minus y. You can change. So we can change with our equations if you want, like x plus y, for example. Okay, that's our graph that's supposed to be. And then we can maybe taking times and then see that which solution we are going to take. Okay. And then we can change all the, I think we can change all the elements. This n, I'm not sure what kind. Okay, n is how many slope fields that we want, okay, in one take. Okay, so 10 is like this, and then let's say 15 like that. So the more you have, then the arrow will be more. Okay. And of course, if you see, we could just like approximate, like, oh, perhaps it's like this. Okay. If we make it like small. Okay. This is the, I think the delta. If we change the delta, maybe changing to 5. Okay, it's become more. So this will be the delta. So we could change in any position we want. Like, for example, if we want to make it in 0, 0, perhaps this is going to be the graph. Okay. The graph, or perhaps this is going to be the graph. Okay. So there are some mathematicians that providing this information. You can open GeoGebra and try by your own, and then you can use many functions, and you can change maybe to trigonometry or any function, as long as it's at the first order, okay, which is the first order here. Okay. Just a quick notes on the slope fields. Okay. Now it means that if we are given, for example, this one here, if you are given, this is the slope fields or direction fields for dy dx equal 0.2 xy, you could see that maybe we can make it here, make it here. This is many solutions, right, that we can make. So according to initial condition, we can fit which solution group we want. For example, this is several examples. Okay, it's not necessarily all the solution, but this is just the books. They are taking some examples for the solution group. Perhaps this one is the solution. This one, and this one here. Okay. Okay. So it depends on initial condition. Okay. And of course, we could see from what we have here, we could see whether the dy dx is in positive or negative. We could say as a function that will be related to our increase or decrease function, right? Okay. So that will be our discussion. So let me just go by here. So if we take the use the direction field to sketch the approximate solution. So for example, our equations is dy dx equals sine y, and then we put into our direction field, and we get this. Okay. And how to get this? Basically the same as we mentioned before. We make a table. We set up some x and y. Try to fit the table, and then approximately draw the slope point by point, okay? Or just go to GeoGebra, finding the slope fields, and just put the equation inside. Okay? So we can construct this, and then we could see that at the point 0, -3/2. Which means this is 1 maybe here, and that is the point here. That we can see that, okay, maybe this is the solution. So the drawing not necessarily to be like perfectly fit and get contact, as long as you can see the patterns, how it goes. You can say, and you can propose, maybe this will be the solution curve. Okay. And again, this will be really useful if the differential equation doesn't have like the solution analytically. Then you can find through graph. We can say that this is our qualitative solution. Okay, we will have a break. Okay. Okay, now we continue. Now from the direction fields or the slope fields, I would like to explain on the what we call the autonomous first order differential equations. So what does it mean? This is what we call that the differential equation that is free of the independent variable. So usually we say independent variable like x. So this means that this dE doesn't explicitly showing that x. Okay. So we can write in general, like we did in the in the last couple of classes. Usually we write like this, right? And then y prime, y double prime, da, da, da. Now we are removing the x. So we say that this is free of this x. So we can write, let's say y prime equals 0. Or we could write dy over dx equal function of y. Just as simple as that. So why this autonomous will be important? Because most of the applications or models in physics or maybe in other fields, they are autonomous, which means they are not changing over the time. So we could say that they are autonomous. So mostly they are time independent. Okay, and within this autonomous, we are going to see some parameter which we call the critical points. But I would like just to show you how we could observe these critical points before I'm going to like describe everything. So let's say we have an example of the dy dx equal 1 plus y multiplied with 1 minus y. Okay. If you see from this equations, we see that the equation doesn't have any independent variable, which is x. It's only have y. So we could say, okay, this is autonomous. And then, if you remember the critical points in the calculus, do you still remember what is the critical points? Do you remember how to find the critical points usually in calculus? How to find the critical points?
You cannot say it's.
Yeah? Yes.
It's when derivative equals 0. Right?
Yes. So we could say, like in the calculus, that when we have dy dx equals 0, we might get the critical points, right? So this is critical points. So the same way, we are going to take this equals 0, and then we get that we have several y here. So y equal negative 1, and then y equal 1. That will be, we call this, okay, we see that this is critical points. But what does it imply? Okay, so let's say we are going to take the graph, and I already copied the graph here. Okay, that's the graph for our maybe let me make it a little bit smaller for this one. Okay, so we can make it bigger. Okay, at least that big. Okay, so in the graph, y equal 1 will be here. If you see this is 1 and this is negative 1, let me just draw the line. Just like similar to asymptote, but this is on a straight line, a horizontal line. Okay. So maybe blue. Okay, this is 1, this is negative 1. So this is y equal 1, this is y equal negative 1. Okay. Okay, now we could say that y equal 1 and y equal -1, they are both acting as an or as asymptotes. So if you see, if we take some interval or we take some approach for some solution curve, so we are taking here, we are taking in the middle here, and we are taking around the curve. So we see that, okay, let's say, maybe if we take this one here, maybe it will make it like that. Okay. So it's getting approaching y equal 1, but never crossing that y equal 1. Maybe it's not really smooth. Okay, maybe that is okay. And then this one here. Okay. And then another one, maybe like that. Okay, perhaps. Although, like I said before, this is our approach to approximate the fitting curve, right? And now we are going to see that we say in between this y equal -1 and y equal 1, we say that this will be stable. So we can say asymptotically stable. And this one here will be unstable. And then to help our observations, we are going to have what we call the phase line. So let me draw here. Okay, let me draw here. So phase line is basically just a vertical line, and then the critical points will be put together here, maybe using different color. So this is 1, this is -1. How do we use this phase line? We are going to take the interval. We're going to take the interval between these two, and then above 1, and then below -1. We can check with some numbers. We can try 0 on the middle, we can try 2, 3 here, we can try -2 or -3, and so forth. And we are going to check whether it's positive or negative. Okay. So let me write again the equations, which is 1 plus y, 1 minus y. So we are going to check, let's say we are going to check y equal 2. Okay, if we check y equal 2, we're going to get a negative, right? Because we have 1 minus 2. So positive, negative will become negative. If it is negative, let's say this is negative, we are going to draw an arrow that is going down. Why is okay. Alright. And then we check in between -1 and 1, let's say 0. We check 0, it's positive, right? So it's positive, we take a positive like that. And then if positive, then the arrow will be going up like that. Okay. And then check if it is like below -1, it means that maybe -2. What will happen with -2? It will be negative. Is it -2 plus negative? It's negative, right? So it's negative. And then we go back down. Oh, wait, it's missing. So what's happened here? So as we can see that if we observe this y equal 1, we're getting an arrow from downside and from upside. We can say when we have this, they both attracted to the asymptote y equal 1. We say that this y equal 1, or the area here, is what we call the stable equilibrium. And this one here that is repel each other, we call the unstable equilibrium. If we see from the curve, as x getting infinite or getting larger and larger, the solutions, they are becoming unstable. But if we see the solution in between here, between -1 and 1, we could see that the solutions, they are getting towards something. Okay? As the x getting larger, they are getting towards something, which means the asymptote. Okay? So this is called the phase line. Okay. Or sometimes we call it the phase portrait. And let me go through some description on what the example is trying to say. Okay. Okay, so let's go through. Okay, so this is explanation on the phase line. So suppose that we have dp over dt, which we can describe as a minus b or a minus bp, where a and b are positive constants. So T and P, we can see that they are the independent and dependent variable. So this is independent This is the dependent variable. Okay, now as we did from the previous page, we can try to make out the critical points, which the dp dt equals 0. Okay. So we see that p equals 0 and p equal a over b, right, will be a critical point. And then same thing, we could check the interval. We could check the interval. So you check the at least 3 interval from the critical points. And then you could say that we can have this 3 interval, and then it has been written down in this table. So we draw the arrow, right? The points down, points up, points down, which means that the p will be decreasing, increasing, decreasing, as it is, I think, very similar to what we have in calculus, right? The function increase and decrease. Let me check. Okay, let me go a little bit here. I just want to copy this and put here. So similarly, if we look here, I have 2 graphs here, which indicates the region R and the subregion. So if we have the, let's say, the solutions so if we take a look on the graph B, okay, we have 3 subregions, R1, R2, R3, and these 2 solutions that has constant C1 and C2, they are both acting like an asymptote here. So if the point is on subregion R, which are I can be 1, 2, 3. We have 3 subregion, and y-x is solution through this point. Okay, through this point, the x0, y0. Then y-x will be remains in this subregion Ri for all x, which means that if it is on R1, then the solution should be stay or remain on that subregion. Okay, and then the solution maybe stays with the R2, okay, because the solution on the R1 cannot cross to R2 like we did in the previous curve. Okay, if you see, we have the asymptote, right? So you see that if we have some specific interval, then the region will remain. Okay, we cannot like removing the interval. Okay. So let me write here, cannot, or maybe the graph of non-constant solution cannot cross the cannot cross the y-x equals c1 and y-x equals c2. And then another thing that we can also try to find out, also from the previous example that I show you, and we call that, if you want to know, it's called the logistic equations. That is really useful for optimization. Okay, if you are interested in like logistics, like or you have interest in data science for logistics, I think this is useful. And then by continuity, okay, because we want to make sure that the functions is continuous, then we need to have the fy is positive or fy is negative for all x in the subregion. So in other words, what does it mean for this positive or negative? It means that within the interval, within the subregion, the slope or the curve, they cannot change the signs. So if it's increasing, then it's increasing. If this decreasing, it's decreasing. Okay. So we say here, fy cannot change the signs in subregion. And then the solution y of x is strictly monotonic. Okay, that's also similar. So it means that yx is either increasing or decreasing. This is as implication from the previous one. So the solution cannot be in oscillation. Okay? So they can only be increase or decrease. And if you remember the monotonic, if you remember what we did in calculus 2, we have monotonic and bounded sequence, right? So we can also see that the asymptote is like a boundary. So we could say that yx is bounded above critical point, let's say C1, as we see from the picture, critical point C1. It means that in subregion R1, okay, so where the yx is less than C1. Okay, so all the solution will be below this C1. It means that the graph yx must approach the equilibrium yx equals C1 as x getting infinite or as x getting negative infinity. You can see from right side or left side. And then the same thing for the C2. So if yx is bounded below critical point, or maybe not below, maybe the middle one first. Okay. The middle one first. Bounded above and below by C1 and C2, which is, this is going to be that interval. Okay. Then the graph yx, they must approach both critical points. Let me make okay. And then a little bit, make it small a little bit. And then lastly, yx is bounded below critical point C2, as C2 is less than yx. So the graph yx must approach equilibrium yx equals C2. Okay. But I think if you understand what does it mean, you don't really necessary to write all of this. But basically what we see is if we have this, then we cannot have any oscillation movement, okay, within the solution curve. Like if this is increasing, then this stay increasing, and we cannot cross this asymptotic line. And if this is in the middle of the region like this, it means that when it's approaching the critical points that is C2, and it will like getting close and close to C2 without crossing it. And if we see that if x is getting infinite, because it's approaching the other asymptote as well. Okay. Okay, as more and more picture, I think we can just giving you this just for observations. Okay. So we have decreasing as we increase, and this is the phase portrait or the phase line. So we can see that it is getting into the A over B, which means that it is, we can say it is very stable because it's getting something that is equaling the critical point again. And if you see from this point here, the second one, if we increase along the t goes to large numbers or infinity, we see that it's getting nowhere, right? It's getting nowhere. We could say that these two here is repel each other, which means that it's very unstable. Okay. And there are conditions where perhaps sometimes if you get getting down, and maybe this is down, we call this as semi-stable. Okay. Well, it's practically in between unstable and stable. Okay. And this is how it looks like. Let me just make it bigger. So sometimes we can have this. So we can say that in A, this is attractor. In B is repeller. And this one here is this semi-stable. So attractor as in make it stable, make it unstable. Okay. Thing once so if we see from the slope fields or directional fields, because of it, this is the autonomous, we can see that particularly they are different and they are the same if we look on the horizontal, right? Because they are free of the independent variable x. So we could see, we could just make the observations through the vertical line. And then another thing about this autonomous is they have the translation property because of it is free of the independent variable x, so we can have the translation property. So in any different interval of x, they will have the same fitting curve. I think that's it for the introduction on the first order. Maybe before we go to the separable equation, let me just go through what we have here. Just an example on the slope fields. So this is dy dx equal x squared minus y squared. Okay. For example, if we want to draw -2, 1, or this point, okay, then practically we are going to find, okay, this is -2 down there, and then 1 is here. So it's going to be around here, that point, right? So perhaps this is going to be like that, okay? Perhaps that is our solution. Okay? We can propose, okay, seems to be fitting with the slope fields, although that will be very depends on how the graph is, okay? If we could make it more clean, and maybe how many partitions do we want, okay, how many pixels for our graphs, that's also very depends, okay? And we say that this is practically our approach for qualitative, it's not quantitative, so it's not really an exact solution. This is approximately qualitative approach, okay, by drawing. And for example, if we take another, let's say 3, 0, so we take 3 is here and 0 is over here, so perhaps this is going to be like that, okay? Perhaps that is our graphs, okay? And we could just take some points and then check within this directional field, okay? So I think that's it. Okay. I think that will be for today. I will move to this one here. This one. Okay, we are going to have a short test, not a quiz, just a post test like usual. I'm using different platform now. I think this is better than the Mentimeter. Okay, so if it is asking your name, please write your student ID. Okay, student ID. Okay. Okay. So please go to the website joinmyquiz.com and then entering the code 547080. I think there are maybe 3 or 4 like really short questions, just to checking whether you are able to check. Okay? Yeah, just use your ID. Yeah, student ID. It's using student ID.
Just student ID.
Student ID. Student ID. If it's asking your name, just write your student ID. Okay. Okay. I think how many we are? I think we are around 40, but I think not all students coming back. Okay, can we start? Can we start? No? Okay, I think we can start, right? We can start. I hope you understand what okay, true or false? Is it true or false? Okay, yeah. Okay, it's false. Okay, Should be the highest one. Please be careful. Okay. Okay. Okay, it should be third order and then nonlinear, right? Nonlinear. Because it has a power of very fast. And within 2 minutes. Checking whether it's linear or not. Okay, what's to the left? What's to the left? Oh, we have 39. Okay. Wow. Okay. Yeah, it's linear. Okay, it's linear. Okay. Okay, do we have another one? Okay, finish. So this will also will be your attendance, and then see you next Thursday. We're going to move to the new techniques for differential equation.